So, good afternoon, everybody, and a very warm welcome to our Circular Economy webinar. My name is Oliver Hasser. I'm Managing Director of INAM, the Innovation Network for Advanced Materials, an organization that is focused on supporting innovators, and that is entrepreneurs, corporates, investors, researchers, experts in the field of advanced materials, and we do that by a number of things. We run startup programs, we run thematic events such as our webinar series, and we also, of course, do matchmaking on a per case basis for our members. We are an international organization with representatives and members from all kinds of countries, Germany, of course, but also the US, Japan, Singapore, and many other countries. And as such, we are dedicated also to help the companies, startups in our ecosystem to internationalize. One of our key topics that we have been pursuing over the last couple of years, because of the great potential advanced materials have, is strengthening initiatives in the area of sustainability/circular economy. And in that context, I want to quickly introduce you to two projects that we are currently pursuing. One is focused on Berlin-based industry and industrial players. It's about driving circular economy in industry. And there matchmake between solution providers, i.e. startup, researchers, or anybody else who can contribute to making a given value chain more circular, and of course, Berlin-based industrial players. This webinar is part of a series that we're featuring in this project, although not directly from the project, but we do have another couple of interesting topics come up in the next months. Besides that, we are also part of a consortium working on the STAGE project, which is the abbreviation for Sustainable Transition to the Agile and Green Enterprise. This is a support ecosystem for European SMEs that want to invest in their sustainability transition. And in phase one of the project, we actually disbursed consultancy vouchers/grants with which you could analyze and prepare your investment projects. And now in the second phase, we are running a platform which is offering matchmaking services, trainings, and access to all kinds of resources, including advisors, particularly also support in finding investors for your sustainability transition project. This could be kind of a CapEx project, like setting up a new production plant or something like that, but it could also be a startup that is bringing to the market or aims to bring to the market a solution that will enhance the sustainability of the clients. To that end, we have a full day of events on the 4th of June in Berlin. The morning is dedicated to investors and discussions around sustainability and impact investments in the current political as well as economic landscape. And in the afternoon, we're doing a bit of showcasing of projects. On the one hand, projects that we support through our own project, or companies that we support through our project, but also the benefits and the aspects services that we provide through the project. So if you're interested in joining, do venture to our website or else to the consortium leaders, G&D Partners website, where you can find more information on this. That's about us, about INAM. And now I want to dive into the project and the topic of today, which is batteries. And I'm super happy to have with us today experts from the Berlin ecosystem who's been working on battery technologies for many, many years, is driving a number of projects in that area, and that will be inspiring us with his keynote in the coming minutes. Welcome on stage, Michael Bojdys. I'm very, very happy to have you here with us today, and I'm very, very much looking forward to your keynote.
Thank you very much indeed. Thank you, Oliver, for the invitation, and everyone at INAM who made this possible. Also, thank you all for joining this call. And I hope that we have a couple of chemists and CTOs in the audience, because there will be a bit of chemistry. But otherwise, I will try to give you a couple of ideas and thoughts about how to think about batteries in general. And if I may just share my screen with you, that would be great. So today's talk will be on pointers towards innovation, circularity, and regional resilience in the energy transition space. As Oliver briefly alluded to, I've got way too many job descriptions on hand. I'm a guest professor of functional nanomaterials here at Humboldt University, where I'm predominantly busy with our own lithium-ion battery startup, Mana.Energy, and I will be sharing some of the technology which we're working on with you. Besides that, I'm a consultant in the R&D space, particularly concerned with multi-stakeholder partnerships, because the majority of the problems that we're facing today are not problems that a singular character can solve. It takes a whole village. So if you feel like navigating to a couple of these links to learn about my work on diversity, on science policy, or indeed about energy materials, the QR codes are provided. Now, I don't need to convince any of you why batteries are important, I hope. But there is good backing for that as well. Flexible batteries and batteries in general are some of the top 10 emerging technologies of 23-24, according to my colleagues at the World Economic Forum. Why is that? Because we are striving towards a quantified self. Future technologies will be integrated into our clothing as close as possible to our bodies. They will monitor our vital functions. They will give us an idea about a better understanding of our environment. And as such, they have to be as flexible as our skin and as durable as our clothing at the very least. Now let's have a look at the broader context of batteries. Batteries are connected to a huge number of topics, in particular via the recycling and second life route. Batteries are key for the energy transition. There will be no other way of addressing the energy transition than via reliable storage technologies, in particular in cars and in grids. There are issues surrounding battery demand and production, which we can possibly address via research and development. And ultimately, and this is the topic of a circularity argument, there's a human environmental cost of battery production. And there is, of course, a market need connected with that, because conventional batteries, as you see them today, they fail on 4 fronts when it comes to customer needs. Number one is, what we need is essentially high performance at low weight. So this is, in fact, the critical factor for e-mobility. At the moment, Tesla cars are on average 1/3 heavier than conventionally powered vehicles. This has implications for performance. What we need as well is, and this is something that I alluded to in terms of smart and wearable electronics, is we need flexibility. The more performant our batteries get, the thicker they get, the more stiff they get, and you don't necessarily want, battery pack integrated in your clothing. Number 3, and this is connected with the weight and the stiffness, is the thermal runoff. Large-scale storage solutions usually have cooling issues, so this is something that we need to address. And ultimately, we need sustainable feedstocks. So majority of the batteries that we are producing today, they are exclusively built on a mix of NMCs, so rare earth metals, which are hard to come by at times. Prices are fluctuating widely, and recycling rates are very low. And I will just give you we are living truly in a material world. And since I think like 2021, there are more mobile phone contracts worldwide than people on this planet, right? So in every single one of your pockets at the moment and the screens you're looking at, there are, of course, rare materials built in. And here you have a rough idea of what we mean by recycling rates on the example of a smartphone. A huge amount of these materials of these elements, recycling rates are below 1%. Yeah, in particular for batteries, this applies to lithium. And if you think about even cobalt and aluminum, recycling rates are above 50% already, something that we consider great. So there is a material challenge to be addressed here. And there are ways around it. So majority of the products and processes that we see today are the ones that just about worked, where somebody filed a patent or had intricate knowledge as a backbone of business creation, and that's about it. It's not necessarily the best way of running things, it's just a way that works. Now, when you think about early TRL developments, there are, of course, ways of running things smarter. When I recently checked my old lecture notes from Cambridge, and it always says up to 15 years is the timeline from lab to market. And this, I mean, like looking into literature, these timelines have not decreased in over 70 years. It's always the same thing. It takes up to 15 years from lab to market. Isn't that insane? There have been massive advancements in production methods, robotics, and big data handling, but we still need up to 15 years from lab to market. So there are ways where processes can help us a little bit. And my colleague Mark Kostras here from NICAN, this is in National Resources Canada, is pioneering one of these efforts in terms of the materials accelerations platforms under Mission Innovation. Jointly, we've also built up the Energy Materials Accelerator Network at BMWK, so the Federal Ministry of Economics and Climate Action, CIM network for energy materials acceleration. And materials acceleration platforms in general encompass an AI and data processing part, high throughput robotics and analytics, yeah, mostly connected to thin layer problems. Because if you think about, in fact, hydrogen production or catalytic reactors, these are all thin layer problems. So usually accessible to surface sensitive techniques. They're also easily addressed by robotics in terms of doctor blading, in terms of printing and so on. In effect, batteries are among these problems that you can put a material acceleration platform to work. I'm not going to be talking too much about that. So for those who are interested in the topic of self-driving labs and integration of fair data into that process, I point you to two white papers that were recently put out. One is on AI and self-driving labs. The other one is on energy materials in the context of European, German, and Chinese cooperation projects and funding opportunities. Now, let's go back a moment and think about why we're using NMCs. NMCs are something that kind of works for us, but there are better materials, in principle, at least on paper. So two technologies that have been pioneered and put forward, at least in scientific literature, and my former PhD student, Guiping Li, has been working on that, among other people. In fact, silicon and sulfur battery chemistries. They have their own problems, but in principle, they will be great. Silicon is one of the most abundant elements in the Earth's crust. You have it everywhere in terms of sand, it's silicon oxide. Sulfur is a byproduct of oil refining. There are huge mountains of sulfur sitting around in Australia and elsewhere. They are so big that in terms of area, that NASA is using their spectroscopy instruments on geostationary satellites to point at that to get clear sulfur spectral lines. They are that huge. However, silicon and sulfur indeed have problems, as I mentioned. One of them is volume expansion. We have it with NMCs as well. The moment that lithium is put into the active material, you get an expansion of a material, and this leads to pulverization of your active after many cycles. The other one is unstable. So especially when you drop your phone and when you subject your batteries to thermal or mechanical stress, the SEI is bound to be broken off. That's essentially dead material. You deplete your active and your electrolyte during that process. And ultimately, all of these mechanical deformations lead also to delamination and homogenization or mixing within the battery. And that's the battery breakdown. Batteries only work because we separate the plus and the minus, so to say. You see it just by the labeling. So thermodynamic equilibrium is the death of a battery. So we want essentially ways how to keep that stuff separated while it is active, while it is doing something. And ultimately, what about sulfur now? Now, sulfur is a tricky one as well. I mean, some of you going back to literature have heard about the sulfur shuttle effect. Sulfur is way too soluble in the majority of our electrolytes, so it will essentially also break down this equilibrium. And I believe it is a material choice that in fact gives us all of these problems that batteries face today. Plus they're toxic, plus they're hard to recycle. So let's think about it in a slightly different way. On the left-hand side, you essentially see how batteries are manufactured in the majority of the processes. Just about all of them work the same way. We take the active material, put it on top of our current collector. Usually we need a conductive additive because that stuff doesn't stick very well. And because it's weakly coordinated components, we also need some binder, some kind of glue. And then we just whack it on, dry it, and we have our anode or cathode. That's not a very good process, is it? Because it's all weakly coordinated. It's sitting on top. The moment you expose it to thermal or mechanical stress, of course it will move or delaminate or pulverize. So let's think about it in terms of marbles. Marbles are not sold by the handful. They would slide, they would drop out of your hands. Marbles are sold in a net. So that is essentially a trick which is now currently explored by a number of players. How do we encapsulate the active material in such a way that it stays where we want it? In fact, one of the processes that we've been looking at is the formation of a three-dimensional network around silicon nanoparticles. What you achieve here is essentially a polymer network, which is diffuse enough that lithium can get in and out, but strong enough that it keeps the silicon in place. The preparation of this polymer network is something that majority of chemists will recognize. This is copper activated Eglinton coupling, where essentially terminal acetylene groups are coupled together to form these sort of honeycomb structures. These essentially encase your silicon nanoparticles nicely, and even when you get the expansion, you have now, in this case, strong covalent bonds keeping all of the individual parts of the battery together. So that is a bonus. Now, I know from Tesla that they've been experimenting with longer chain polymer binders, however, one-dimensional ones. Now, this is sort of like trying to keep things nicely held together by spaghetti instead of a soup. It works better, but it, of course, will work better with a two-dimensional or three-dimensional SIP. The respective electrochemical performance indicators you see here. So routinely, we stay above the 2,500, 3,000 milliampere hours per gram of material. So this is just about the theoretical maximum. There is a bit of a drop-off, but there are ways of improving that. If you contrast that, for example, with PVDF, classical binder, that stuff doesn't survive at all. So here is a clear bonus of just using this type of chemistry. Now, we've been discussing previously in the introduction section, the sulfur shuttle effect. Ideally, you want to give sulfur the same kind of binding network, and ideally you want to make sure that sulfur is less prone to diffuse out. So one of the chemistries that we've been looking at here is, in fact, this imine-based network. So you can see here again for the chemists or the CTOs in the audience, you see this is essentially a heteroatomic conjugated network. So of course it's a much more interesting energy landscape. So sulfur has the opportunity to bind reversibly to certain sites in this polymer network. As a result, what we see here is not only do we limit sulfur diffusion within the battery, we also achieve pretty much just about the theoretical optimum of what we could store in terms of lithium sulfide species. So we're routinely, even after 500 cycles, above 800 milliampere hours per gram. The question is, of course, now we've got the cathode side sort of lined up nicely. We've got the anode side where we limited the sulfur shuttle effect. Let's pull these two together. Here we have essentially the imine, the lithium sulfide, sulfur cathode on the one side, and our polymer silicon anode on the other. And as you can see, the concept works in principle. So after the 100 cycle, we're still way above 300 watt hours per kilogram, which is a pretty good thing. So this is again TRL, let's say free. This is coming out of a lab. Of course, it needs an application, right? Some of you, especially from I don't know how widely spread that was, but especially the German audience knows, of course, marketing batteries is far from easy. In the 90s, the Duracell bunny was all over TV. It's an absolutely stupid way of marketing batteries, but it shows one concept, namely longevity. And this is in fact something that we want to advertise here as well. These batteries will be able to either perform longer at the given parameters or have a higher peak output for the same amount of time. But a good example of the use of such high energy density batteries would indeed be wearable electronics. So here you can see an example of illuminated sportswear or street jacket that is championed by our LOI partners at Inuru GmbH. These guys produce sustainable OLEDs and want to integrate them into wearable clothing. At the moment, these LEDs are powered by classical power banks. These things are stiff, they're fairly heavy, but you've got it in your pocket. It still works, but of course it will be much nicer with flexible, lighter batteries that you don't feel at all. So this is a good beachhead market indeed for such battery applications. Another one, and this is really future music, is to really think about how do we integrate such high performance batteries into EVs, because this would be indeed the game changer. If we could get an EV weight down by 30%, there's absolutely no argument whatsoever to be made for conventional combustion vehicles, other than, well, it's an existing industrial stakeholder. So for those of you who would like to know a little bit more about the general KPIs of the technology, our CEO, Barbara Baltzarova, and her tech is highlighted in these one-pagers. Here the QR codes provided. If you're more interested in the general science behind this, I invite you to reach out to me. We have had a great team from all over the world working on energy materials questions. I mean, like sometimes it's really, well, sometimes, most of the times, it's very interesting to get the perspectives, in fact, from other parts of the world, because the market for your idea is not necessarily where you develop the tech. I will just give you maybe one idea. At one of the World Economic Forum meetings, I ran into a colleague who also studied in Cambridge, and he introduced himself as Dr. Toilet. Of course, that was not his name. We bonded over having studied in the natural sciences tripos in Cambridge. I found out that he was one of the top 10 richest men in India. I'm top 10 richest nowhere, right? So what's the difference? Well, he essentially understood that in India, majority of the rural communities are not connected to sanitation, right? And he started via governmental contracts and via his own companies to deliver biodegradable, biobenign toilets to these communities. Imagine one of the tweed-wearing, pipe-smoking colleagues from Cambridge. They would have not come up that such a problem, technical problem and societal problem even exists. So diverse teams make for better decisions, and they also enable you to crack into different markets and bring their own perspective. And I think this is something which we definitely try to live here in Adlershof. And I'm sure you do in your own companies as well. So thank you very much for your attention. I will leave you with this. Feel free to ask any questions maybe after the event, and reach out to us if you're interested in the tech. We're always looking for collaborators, and I will point you to Barbara Baltzarova, who will be heading the team starting on the 1st of May. Thank you.
Thank you very, very much, Michael. A very inspiring and insightful presentation. Please do reach out to Michael if you have questions after the event, but also if you have questions now, feel free to ask. We have a bit of time allocated to Q&A. If there is any question that is really pressing, please open your mic. We are small enough a group that you can actually just ask it directly. If you're shy, you can also put it into the chat. And whilst whilst we wait for people to ask questions, I've got one here, which is a bit about the market for battery. You've indicated some of the use cases, and obviously, electric mobility on the ground is certainly one thing that can greatly be enhanced with better battery technologies. But there's other use cases, like for instance, for drones and other flying objects. But how do you see the market development at the moment? We're talking about batteries now that we also saw, a huge insolvency of a very promising new battery supplier from Sweden. What's your take on the market development at the moment, Michael?
I think it's important to understand your niche and energy demands. I mean, like, let not, especially to the CTOs in the call, let not marketing confuse your knowledge, right? Meaning batteries are not a universal panacea. You are structuring your product to a certain power output requirement, and that's about it. So I think like overselling your batteries that they are useful everywhere is a fundamental fallacy. I mean, I would just give you maybe still one more supply slide. Looking really at the use case scenario. At the moment, what we pretty much see is that majority of the products out there in the market lie along this dotted line. You have flexibility or relative flexibility at low capacity. At high capacity, you become fairly inflexible. But it's not just because of the stacking and the arrangement, it's also because of the casing. Or, if you think about IoT, CMOS, medical implants, these batteries are fairly slim, fairly small. They also don't need large capacities and power outputs there. The moment you go to large scale energy storage, of course, it's inadvertently you will become inflexible, right? So it's sort of like hitting that beautiful sweet spot over there, high flexibility and high capacity, where you don't necessarily cater to a specific existing market. You can improve all of them. You generate a fundamentally new market niche. That is the point, right? Like nobody would honestly try to think that based on power bank technology, you could power, high energy demanding sensors in your clothing. This is a completely new market niche. So understand your market niche is pretty much the idea here. I think the technologies which we have right now work fairly well, with one caveat. The caveat being that if you are relying on NMCs, you will always have a supply problem. So I'm not quite sure whether I'm answering your question. The question regarding the use case scenario is really look at the output you need, look at the flexibility you need, and consider really this graphic here. The new battery tech will definitely be opening up new use cases, and here we could potentially lead in Europe.
Well, yeah, thank you very much. That does give a good answer to that and a very good outlook on where and how the market, in particular in Europe, could develop. There's another question in the chat, but also a hand raised. So Michael P, maybe you go first with your question.
Yeah, thanks, Oliver. Thanks, Michael, for our presentation. Well done. My question is towards a little bit other batteries technologies. Like I know that China invests a lot in sodium-ion technologies, batteries. What do you think of this? Jerry, what do you think of sodium-ion battery technology, and what do you think is the best use of it?
Sodium-ion technologies are quite interesting. I mean, the classical argument was that fast charging isn't possible. I mean, like takeaway message, of course, everyone who understands the periodic table of elements knows that sodium will diffuse slower than lithium, period. Yeah, you can't overcome the laws of physics. However, there are some clearly interesting processes developing there. So sodium-ion batteries, in particular in stationary storage, I see great potential there. So because I mean, like where you don't necessarily need high C rates in charge discharge, this will be a winner. There will be overall, I think. I mean, like in the current paradigm, sodium-ion batteries on average will be heavier compared with lithium MC. So stationary storages is potentially where they would win out. So this is at least like the trajectory which I sort of see at the moment. There are a couple of really alien use case scenarios which I've heard about. This will not be a massive market niche, but for example, batteries powered by seawater on its own. This is not a massive use case, right? But I mean, especially when you think about completely new market niches where a certain electrical gadget springs into life the moment it's connected to seawater. I've seen a couple of these concepts where people were at least theorizing about integrate LED into floating garbage or plastic, right? A small battery that only starts working the moment that it sees saltwater uptake. The moment it forms garbage patches, it will be much easier to track. This was just one particularly crazy use case scenarios where I thought like, oh my god, yeah, this would be a great use case for sodium-ion batteries. But I think like in realistic terms, stationary storage is the way forward.
So like big, huge, bulky stationary storages for like whatever, like solar panels, like or
yeah, I mean like this is at
wind
least
power,
this is at least where it's playing to its strength, right? Because I mean, if you think about it, you don't need massive C rates there. You just need essentially storage capacity for overproduction of, let's say, a wind farm or something like that, right? So
Right.
here
Yeah.
it would work really well, and it's playing to its advantages.
What do you think like those EVs, but like more like city, like those small Nissan Leafs, you know, that drive like around 50, 80 kilometers? Do you think that might work for sodium, or is it going to be too heavy?
I mean, like this might be too heavy, but if you think about tuk-tuks, yeah, especially in Asia, or these electric rollers, you know, they don't have to go far. This might work as well. I feel like in terms of just a pure calculation, you know, weight per performance ratio. Does that answer your question, sort of?
Yeah, thank you. Thanks, Mike.
Thanks. There was a question regarding regulation.
Exactly.
I think like for consumer electronics, ISO 9001 works for everyone. The moment you want to go into EVs, the big one is IATF 16949. So this is something which is definitely way harder to get. And here you are talking about like if you really think from the startup perspective, and Mana.Energy, for just as an example, will be dabbling in consumer electronics for the foreseeable future, because getting the IATF 16949 is somewhat tricky. And we see the trend from Chinese EV manufacturers. The entire supply chain has to be IATF 16949 compliant. So we will not be getting there anytime soon, but I'm sure certain participants in the call and definitely in the market space will be getting there sooner.
Thank you very much. Let's switch to the next speaker. We have a bit of time after that also for further questions, but I don't want to keep Karl waiting much longer. Karl, thank you very much for joining us also from Ireland, I take it, right?
I'm Irish, but I'm in the UK.
You're in
That's
the UK.
where
Okay.
our company was started. We started in Ireland, then New York, and now we're in the UK. So it's a bit of a journey so far.
Sounds interesting. I mean, follow the money, they say, right?
Yeah, yeah, exactly. Yeah.
Right. Now, Karl is presenting Inition, a battery startup. I'd like to invite you, Karl, onto the virtual stage and present Inition to us.
Okay, thank you very much. Thank you, Michael, for your presentation. It was very interesting. And you're kind of interesting to see Mana are working in the same kind of areas as us. But I think the technologies are complementary. But we see a big need for change in production technology and the chemistry, and an acceleration of development of battery technology in general. But can you see my presentation there? Okay, good. So I'm glad you did the chemistry bit, Michael, because I'm not a chemist. Boris and I were the co-founders of Inition, and we started 13 years ago in the battery industry. And this was before batteries became the big thing they are now. And what we were doing, we were developing high performance batteries for niche markets. So kind of aerospace and other kind of communications applications. And in the journey of developing those batteries in Korea, we recognized a bigger problem, which was how the batteries themselves are produced, that they're produced extremely inefficiently, and there's a big opportunity there to reinvent the production process itself, to bring down the cost, but also make it more sustainable, which is what we're talking about here today. So this is what we're making. I always put this up first because some people don't have a full understanding how the battery is put together. I think this audience is a bit different. But this is what we're making here in our lab in Oxford. We're making anode and cathode. It's coated foil, either copper or aluminium, and we coat both sides and then we make it into batteries. So we can make any form factor of batteries. We can make cylindrical, pouch, prismatic, and we also make any chemistry. So we've made silicon. Mike was talking about, we've made graphite, NMC, LFP. We're chemistry agnostic. So why are we focusing on the electrode? The reason is that the electrode is the most expensive part of the battery to make, but also the most environmentally unfriendly and energy inefficient part of the battery. The production process itself is extremely inefficient, especially as we scale up battery production for the green transition. So here's kind of a summary of the main problems. The first is the cost. So the margins for even the biggest manufacturers are razor thin, and anything that goes wrong in production can wipe out their profits for the year. The other thing is sustainability. So what we're focusing on, rather than gigascale and the EV market, which, as we've heard, very difficult to get into, we're focusing on verticals. So the battery market we see changing, and there's a lot of verticals that are demanding application-specific batteries to suit their needs. And at the moment, they can't get them because gigascale production is set up to serve either EV market or stationary storage market. And there isn't really kind of a middle ground for them. But the problem is, as you scale down production from these gigascales, the efficiency becomes much less, and you get huge increase in energy consumption, and the efficiency of the machinery and everything reduces by a huge amount. So an example here is 300 kilowatt hours to make 1 kilowatt hour of batteries, and that leads to a very high carbon footprint. So the other problem that we're trying to solve is energy dependence. So if 80% of something that's critical for your product comes from one specific location, it's a big problem. And we need to localize production as much as possible. One of the solutions to that is to make the production itself more efficient and more flexible and modular, which is what we're trying to do. And then finally, I touched on already, inflexibility. So because large-scale battery production is set up for the EV market, these applications that I'm talking about and Michael was talking about, so for us, it would be subsea applications, aerospace applications, performance automotive, all these kind of applications that need specific batteries. They can't get what they need because their demands don't fit the economics of the gigafactory system. So our solution, focusing on the electrode, is a complete reinvention of the process from first principles. And with it, we've been able to achieve over 25% reduction in the total cell production cost. Our machinery is also 10 times smaller. So we have flexible modular lines. And we've been able to eliminate toxic solvents and forever chemicals. So where conventional battery production uses NMP and forever chemicals, we use water and water-based binders, even for water-sensitive materials like NMC, high nickel NMC. And then finally, because we're enabling the production of very thick electrode while maintaining the power capability, it allows us to put 20% more energy into the battery with purely this mechanical change of making the electrode thicker. So the process is mixing coating and drying with the inclusion of this step called particle alignment. And that's what enables the thicker electrode, which I'll talk about here. So there's two main things here. The first on the right is what we call particle alignment. And this is something we achieve with a combination of steps in the process. And what we're doing is ordering the particles, the microstructure of the electrode, as we're coating it onto the foil. So with conventional process, you can see, go back to Michael's marbles. The marbles are just randomly arranged as they lie, as they're deposited upon the foil. And this creates these kind of tortuous pathways for the ions to travel from anode to cathode. And what that does is it limits the power capability of the cell itself. Now, what we're able to do, we don't put the marbles in the bag yet, but we're able to line the marbles up. So, but by doing that, we create these highways for the ions to travel much more efficiently through the electrode, through the electrolyte to the other side of the battery. And that allows thicker electrode, which means less inactive material, which means a much more sustainable cell, because you want less copper, less aluminium, less separator, and you want more of the good stuff. The meat of the battery is the black active material that adds to the energy density. So that's what we're doing with alignment, enabling low tortuosity, high loading electrode. And then, as you know, projects like Northvolt, new battery projects, they have a very high scrap rate. But even mature gigafactories have a scrap rate of between 5 and 2%. And if you think about that in terms of electrode, that's a huge amount of electrode wasted. And the difficulty with conventional process using NMP is that it's very difficult to separate the black mass from the foil efficiently. And this is kind of like a side thing we've done. This isn't our main focus, like the recycling. But what we do is we enable other companies to make the recycling process easier. And one experiment we've done is being able to coat the electrode, complete the electrode, and then after completing the manufacture of it, we can recover the metal foil completely pristine and save the black mass and separate them perfectly, either for reintroduction into the process or for easier recycling. But our goal is to make the process circular. So you can see here, this is the conventional process on the left. Using NMP, any scrap that comes out of the process, mixing, coating, drying, slitting, it goes into a non-recyclable waste stream that needs to be disposed of. And then at the end of the process, you have cell testing. And if the complete cell doesn't pass, then you have another waste stream that has to be disposed of. And this is a huge cost, but also a huge environmental burden. So what we're doing is we're trying to make this more circular. Using water and using water-based binders, we're able to recycle the scrap much more easily. Black mass, we have a process where we have it dissolved in water, and then we have a process where we can separate the black mass from the binder. And the ultimate aim will be to put that back into the process again to make new electrode. So this is an example of the cost savings possible in terms of materials. By doubling the loading of the electrode, you can make a 21% saving in the overall cost of production. But then in terms of energy, you can save almost half of the energy by using our process, because we're getting rid of very energy intensive drying ovens and energy intensive solvent recovery systems. In overall terms, we're making a 40% saving in the total production cost of the electrode, which is very, very important, because if you're trying to make something more sustainable, no one's going to adopt it unless you make the economic case for it. But what we're doing is we're saving the manufacturers a lot of money, because from talking to them, we've kind of gauged a huge bias towards cost saving over sustainability. But if you can give them both, then you're onto a winner. So to summarize the recyclability, we're eliminating PFAS and we're eliminating NMP, and that will make circularity in battery production much more achievable. And this is a schematic of where we're improving and where we are operating. So this is mixing, coating, and drying. This is where we work. And everything upstream and downstream stays the same for conventional manufacturing. But with our process, we're making improvements in 6 of the 10 steps defined here. So we have IP. We're the first ones to work in this particular area of particle alignment. There are universities that are working in it after us, but we have the kind of priority in terms of protecting it. And the roadmap. So we're in the market already. We have a lot of experience with Korea and working with customers in these verticals that I talked about. By the end of 26, we hope to have commercial electrode production up and running, and we're going to work with assembly partner to deliver application-specific cells to customers. And then by 28, we're going to have full cell production here in the UK, the most sustainable cell production site in the world. And it's going to be downscaled because we're not aiming for gigascale. It's going to be 50 megawatt hour production capability, but extremely efficiently so. And yeah, that's Inition. And if you have any questions, I'd be happy to answer afterwards.
Thank you very much, Karl. Very impressive technology and the company thereby. Yeah,
Thanks.
open floor or mic for questions now. Michael.
Thank you very much, Karl. Just a quick one. So regarding the process, it's a dry process you mentioned, right?
It's between wet and dry, we say. So the slurry is very, very high solid content.
So it means
yes.
essentially high viscosity, I would argue. So
Yes.
so the application process itself is that. Can you go into a little bit more detail how you apply the high viscosity slurry onto your current collector, or is that proprietary information?
No, I can tell you a little bit, and then if you want to know more, we'll have to hire you probably. But the method is injection.
All right.
So it's a kind of a high power injection system, and we're injecting both sides of the substrate at the same time.
Got it. Now, because I just recently, I don't know whether you came across that. So the MET University of Münster, they essentially reported on a PTFE binder based dry processing of lithium ion battery slurries. I was just wondering to what extent you have there some overlap. Might be worth. I mean, like I can send you the link to their press release in the chat, but it might be worthwhile checking like what the differences there are. That's really super cool. Thank you so much.
Yeah, no problem. For that sounds very interesting. And we like our main competitor probably is the dry processing.
Yeah.
We would see the differentiator as being the microstructural control to enable the high power capability.
So,
go ahead.
No, I was just wondering, in terms of this high pressure injection of the high viscosity slurry, is that a limiting factor in terms of how many square, what kind of area of electrode you can produce per time unit?
No, the production rate is pretty high, even at our scale, which is we're lab pilot scale. We can do 10 meters per minute already.
Great.
But we can modify the pressure that we apply, and we're not shackled to the ovens, which is another big thing, which doesn't that's not a bottleneck for us.
Wonderful. Thank you very much indeed.
No problem.
Michael P has another question.
Listen, Karl, good presentation. Thank you. Got a question. You said you will do cell production in the UK. Why in the UK? Is there because might move somewhere where it can be cheaper to produce?
Yeah. So the UK not battery production friendly, I have to say, but the need in the UK is for security of supply, and our customers in particular, so security and defense, they want batteries produced in the UK, and it's not negotiable for them. They've woken up to the huge exposure they have to China. like more and more systems are battery powered. A lot of industries are run on batteries, but particularly security and defense. And if China cut that off suddenly, they'd be completely exposed. And that's why the UK is important to make the batteries there.
Right. Thanks. Makes sense.
Yeah. Like the problem with the UK is they don't have the experience in making batteries. And a lot of making production successful is in the know-how. And that's in China and Korea and Japan. And we have our experiences with Korea, and we're working with Korea to bring that experience to the UK with our production technology. And that way, we think we can make it work, even with higher energy and labor costs.
Right.
And maybe
So you said like Korea is good, but how about any in Europe, where Europe also is not that good as Korea sort of?
No, the skills, like if you look at any of the big productions in Europe, it's Korean, Japanese, or Chinese players, and there are a few projects in Europe that are promising, and hopefully they'll succeed. But up to now, none of the big projects have succeeded, and it's because of this lack of know-how that isn't in Europe at the moment. We need to build it.
maybe just, I mean, like Karl, sorry if I jump in, but I mean, maybe as a highlight, if you look at UK is a great example how manufacturing can be done in Europe. If you look at the success story of ARM, chip manufacturer, it's essentially, it was a political decision back in the time to situate them in Cambridgeshire, and via essentially tax reduction and a smart local government policy, it is doable. And I'm sure that Peter Bruce and others in Oxford will go to great lengths to make sure that such a success story is possible again. Yeah.
Yeah, exactly.
Well, that brings me to two questions. One to Karl. Given the super international experience of your startup, I would really like to invite you to one of our webinars / sessions on internationalization as a use case. Would you be up for that? Because we integrate that in our startup programs regularly, because we
sure.
think that you have to think internationally in the advanced materials space. And then secondly, that actually this one is going to Michael B. You've been both in the UK as well as in Germany. Why at the end of the day did you settle for Germany to pursue your battery interests, and particularly Berlin?
Sometimes you have to trust the flow, as a colleague said. I mean, like, I'm not sure, Karl, to what extent your ping pong around the world was always a predetermined decision. Sometimes you just, fall into an energy landscape minimum and you stay there because overcoming the next barrier will be just too tricky. I think but like really now in terms of strategy, Germany is trying hard to facilitate startup culture, also in the deep tech sphere. I mean, you with INAM are a great example of that. Whether that's always successful is a different thing, because I think we ultimately have a difficult angel and VC scene here in Central Europe. I remember one event, a startup event, where a Deutsche Bank person was there and essentially said like, oh yeah, we invest in, I think he even said, we invest in startup companies with a revenue of 20 million euros. And I felt like, that's not a startup. Okay. What are you doing here? Right. So it's a completely different setup. So it's way more regulatory heavy. I think there are better places. What defines this here is they're trying. So there is good avenues. There is also good funding base to get things started, but ultimately you will need to internationalize, and you will need to diversify income streams. So relying on one source of funding, especially if it's governmental funding, it's not a winning strategy.
That of course is true. And maybe one remark towards Karl. If you need any connections in Japan, that's actually our second biggest geographical footprint as INAM. So if that can be of help, do let me know, and I'll try to get you appropriate contacts.
Definitely, yeah. Because I think Japan is quite a difficult place to work for Europeans, because it's so different. So any help there would be very welcome. Yes.
Great. Last chance for questions to either of our presenters. Feel free, Michael and Karl, to put your LinkedIn profile into the chat so that people can hook up with you after the event. And with that, I would like to close the session, give you a short hint at our upcoming circular economy webinar, From Waste to Architecture, Rethinking Circular Economy in Construction, on the 6th of May, again, the Thursday, 12 o'clock. And I'd be happy to also point you to our new website. INAM has rebranded. Sign up for our newsletter to stay on top of things that we're doing. And if you know any interesting startup that could benefit from an acceleration program specifically geared towards advanced materials, please feel free to refer them to us. We are recruiting currently for our ATMACOM Advanced Materials Competition, which is targeting startups between TRLs 4 and 6, so around industry prototype / POC. And that will be held online as well as a couple of days in Berlin in June and July. With that, I'd like to close our session today. Again, many thanks to Michael and Karl for the very insightful presentations. Great advances you've made, Karl, already. You also, Michael, but I keep my fingers crossed that then from May onwards, Mana.Energy is kickstarting its development. So very curious to follow up on that and see a Berlin-based startup in the battery space grow.
We'll try our best. Thank you again, Oliver, Maria, and all the people at INAM for organizing this event. And thank you all the participants for the great input and the questions. Thank you.
Thank you very much and have a great afternoon.
Thank you too as well. And yeah, have a great day. See you. Bye-bye.
Thanks, guys.
Bye.